Test, test, test. So here is the practice test for Chapter 2, Section 5. This is Part 2 for limits. So hopefully I can get through this pretty quickly. If you have any guys have any questions, please let me know tomorrow. Okay, let's jump right in. Use the squeeze theorem to evaluate this limit. I have absolutely no idea what this is. So when I plug in, so let's use the squeeze theorem. We start off with what we know. So the absolute value of sine of 1 over x is less than or equal to 1. We know that sine is less than or equal to 1. So then, second step, we're going to multiply both sides, let's do that in a different color, by what we want to be inside this absolute value sign. So that is absolute value of 1 plus cosine x, and whatever we do to one side, we do to the other. So that's the absolute value of 1 plus cosine x. So that means that when we multiply these two, then we get the absolute value of 1 plus cosine x times sine of 1 over x, that's our original function, is less than or equal to 1 plus cosine x. So we're going to split this inequality into two things now. So we're going to say, let's keep my colors the same. I have 1 plus cosine x times sine of 1 over x is less than or equal to the absolute value of 1 plus cosine x and is greater than or equal to the negative version of absolute value of 1 plus cosine x. So now we have this squeezed between two things, and we can evaluate using our limit, which is x is approaching pi. So if I plug in pi here, cosine of pi is negative 1. So 1 plus negative 1 is just 0. Same thing over here. 1 plus negative 1 is just 0. So that means that the middle term has to be equal to 0 as well. So that's using the squeeze theorem. All right, 2. Let's try a different color. Using what we know, so the two ones that I'm asking you to know are sine x over x, the limit as x approaches 0 is equal to 1, and the limit as x approaches 0 of 1 minus cosine x over x equals 0. So those are the two that I'm asking you to memorize. So let's try this out. This is factor the denominator. That's a nice hint. The limit as x approaches 0 of sine 5x over x times x minus 1. We're going to split this up into the limit as x approaches 0 of sine of 5x over x times 1 over x minus 1. Now, this is just the limit of the product, so if we know what the product is, this is 5. If I plug in 0 here, that's negative 1. So my answer is negative 5. Okay, that's pretty straightforward. B, hint factor the two expressions. So when we factor these, that is the difference of two perfect squares, so that's 1 plus cosine x and 1 minus cosine x over 2, let's factor out an x, so that's x, parentheses, 2x minus 1. Now, I'm going to do a little bit of a rearrange here, and I'm going to write this as the limit as x approaches 0 of 1 minus cosine x over x times, that's these two pieces. Well, what's left? 1 plus cosine x over 2x minus 1. I know what this is. This is 0. And then if I plug in 0 here, I get 1 plus 1 over negative 1. So 0 times negative 2 is just 0. So that's using that cosine value that we know. All right, 3. Show that f of x takes on the value 0.4 on the interval 0 to 1. So this is the intermediate value theorem. So using the intermediate value theorem, we're going to find f of 0. So if we plug that into our calculator, we don't really need to, that's 0 over 1, is 0, which is less than 0.4. We plug in 1. We plug in 1, we get 1/2. That was pretty easy. That's greater than 0.4. So if we know that f of 0 is less than 0.4, and f of 1 is greater than 0.4, remember what these three dots are. That means therefore, there is some x such that f of x equals 0.4 on the interval 0 to 1 by the intermediate value theorem. That's using the intermediate value theorem. All right, 4a, show that this function has a 0 in 1 to 1.5. So we go, what is f of 1? If we plug in f of 1, we get 1 out. So that's obviously greater than 0. If we plug in f of 1.5, that is negative 0.54, which is less than 0. So we just showed, again, therefore, there is some value x such that f of x equals 0 on the interval 1 to 1.5 by the IVT intermediate value theorem. Okay, so that question is very much the same. So B, use the bisection method. Bisection means cut in half. So we're going to cut in this half to a 1/8 length interval. So halfway between 1 and 1.5 is 1.25. So f of 1.25, if we plug that into our calculator, we get 0.42, which is greater than 0. But if we look back, that is less than 1. So we just narrowed our interval down. So we have some 0 between 1.25 and 1.5. That's not 1/8 away, so we're going to cut it in half again. So halfway between 1.25 and 1.5 is 1.375. So 1.375, we plug that in, we get 0.00373, which is still positive, but it's smaller than 1.25. So that tells us that to be 1/8 away on the interval 1.375 to 1.5 contains the point where f of x equals 0. So that's the front side. So flipping it over to the back side, starting with number 5, what three criteria must be met in order for a function to be continuous? Okay, so in order for something to be continuous, the limit must exist and the limit as x approaches some number from the left is equal to the limit as x approaches c from the right of our function, which is equal to just f of c, which means we just plug in c, we get that number out. This is true, then that function is continuous. So then what are the three types of discontinuity? So one is removable. Those are our wholes. We have non-removable discontinuities, and those are our jumps. And then our last one are infinite discontinuities, and those are our asymptotes. Okay, so those are our three different types of discontinuities. 7, discuss the continuity of f of x. So if I type this into my graph, which you can see here, I get a graph that looks something like this. So it looks like a parabola. And if I examine this domain a little bit, the domain here, x squared plus 9, has to be greater than or equal to 0, right? Because we don't want any negatives underneath the square root. So if you subtract 9, and we took the square root, well, we're just taking the square root of a negative number, which means the domain here is all reals. Because the domain's all reals, there's no spot where I can't be. Therefore, this is a continuous function. Now, just as a note, if I asked you, and all I did was switch the sign, if that was x squared minus 9, then we have this completely new, different graph, which is discontinuous. And it's discontinuous from -3 to 3. And you can see that because what number between -3 and 3, we get negative numbers underneath the square root sign, which is what we don't want. And this would be a jump discontinuity. All right, for 8, discuss the continuity of f of x equals 1 over x. So we know, or should know, that this function looks like this. That's our parent function. So there is an infinite discontinuity at x equals 0 because there's a vertical asymptote at x equals 0. All right, number 9, sketch the graph. So if I'm sketching this piecewise graph, where important part is 1. So I have my parabola here, looks something like this. And then I have this line 2 minus x, so it would be here, then down 1 over 1, okay? And then down 1 over 1. So there's my graph. At each point of discontinuity, state whether f is left or right continuous. Well, this function is always continuous. There is no discontinuity, even though it looks like it has one, because the limit as x approaches 1 from the left of f of x equals 1. So from the left, we get 1. Also, the limit as x approaches 1 from the right of f of x equals 1. From the right, I get 1. And f of 1 is 1. All three of these are true, therefore, this is continuous. Okay? So be sure you know how to do something like this. Figure out if it's left end or right end continuous, which is what we're going to get on number 10. Now, if you are watching this, no left, right. I'm not going to be asking you a left or right continuous question on the test because frankly, after discussing this with a couple other people, this is a very little talked about and often confusing thing to talk about continuity. Left end point continuous or right end point continuous is what it's really getting at. So if I'm finding a value for c such that g of x, which is our function, is left end continuous. Left end means coming from the right. So if you are coming from the right, that means we're looking from our positive values. We want to know where the limit as x approaches 2 from the right of g of x equals g of 2. So what we want to do is we want to set this, plug in x plus 2. We're going to plug in 2 here, which is 4. 2 plus 2 is 4. So we want to set c of 2, c of x, equals 4, or c equals 2. So in order for this to be left continuous, coming from the right, that means we have a left endpoint. So likewise, for something to be right continuous, we are coming from the left. So if something is right continuous, it means it has a right endpoint. So we would look at the limit as x approaches, well, what is our negative term in here? Or our right term would be -1 from the left of g of x, and we want that to be equal to g of -1. So again, if we plug that into x plus 3 here, we get -1 plus 3 is 2. So we want that to be equal to 2. So c would have to be c of x, c of -1 has to be equal to 2. So that is c equals -2. So in both of these, we're using each given piece of the piecewise, which is super confusing, to find out what the value is. This will not be on your test. Hopefully everything else that we went over today clarifies some things, and good luck.